Hello, so in this video we are going to go through theme 2 homework, which is all about permutations, combinations and some conditional probability in there as well. So first question, we've got 6 people standing in a line. We've got Alice, Brenda, Caroline, David, Edward and Frank. And we're asked how many different ways can these 6 people stand in a line if Alice, Brenda and Caroline have to stand together. So these 3 people have to stand together. Well, just remember, let's call them A, B, C and D and F. These are my 6 people, and I want them to stand in a line such that these 3 people, so Alice, Brenda and Caroline, the A, B and the C of the group, they have to be together at all times. So effectively, I'm going to treat these as one object. Okay, so I'm kind of like gluing these together. So effectively, the number of distinct objects I've got, well, there's that one in red. Okay, these 3 people in red, I'm treating them as one object. But then I've got D, E and F as well. So in other words, I have 4 objects that I'm going to arrange into a line. So therefore, the number of ways to arrange 4 people into a line is 4 factorial. Okay. Now that's not quite enough. So it's not quite enough to do 4 factorial because you've got to remember that for each of these 4 factorial ways of arranging these 4 objects in a line, A, B and C, in other words, Alice, Brenda and Caroline, they can all stand in different orders. So I've got to consider the number of different ways of ordering those 3 people in a line as well. So basically for every 4 factorial ways there are of arranging these objects, there's going to be another 3 factorial ways of arranging A, B and C within that kind of sub-arrangement, if you like. So it could be CBA, BAC, ACB, you know, those 3 factorial ways of arranging for all of those 4 factorial different orders. So therefore, in order to work this out, I'm going to bring my calculator in. And you can see that I'm just simply going to do 4 factorial. So I'm going to go 4. I'm going to look on my calculator for the factorial button. Now on my calculator, it is up here. So if you see, it is literally just above the x to the minus 1. It's in yellow up here. So therefore, in order to find that, I'm going to go Shift and then click that button there and it'll bring up my factorial. Then I'm going to do times 3 factorial. So 3 factorial. Hit enter and I get myself 144. So that will be my answer here. So I'll put it on the dotted line, 144. Okay. Part 2 then, how many different ways can the 6 people stand if Caroline and David do not stand next to each other? Well, think about this. Sometimes with kind of these ordering arrangements and permutations, combinations, probability stuff, sometimes it's easier to work out the thing which you don't want in order to get the thing which you do want. So let me show you what I mean. I don't know at the moment how to do this because it's asking for Caroline and David not standing together. So I actually don't know a technique to do this directly. I don't know how to calculate the number of ways such that Caroline and David do not stand next to each other. But I do know how to calculate the number of ways for Caroline and David actually standing together. Okay, so if they did stand together, I know how to calculate that. In fact, it's very similar to what we did in part 1. So in other words, I'm going to take my A, B, C and D, E and F. So these are my 6 people. And basically I'm going to say, well, look, I'm basically just going to say, those 2 people there, I don't want them standing together. So let's work out the number of ways of arranging them such they do stand together. Okay, so the number of ways of arranging them such they do stand together, we'll have a look. There's 1, 2, they're glued now. C and D are glued as one object. So that's 3, 4 and 5. In other words, there's 5 factorial ways of arranging these 5 people in a line. But for then every one of those 5 factorial ways of arranging those 5 people in a line, C and D could be round the other way. In other words, there's 2 factorial ways of arranging those 2 people. So that would be the number of different ways of arranging the line such that Caroline and David do stand together. But I want the number of ways such that they do not stand together. Okay. So in order to do this, I'm going to think, well, the total number of ways of arranging these 6 people into a line, okay, with no conditions at all, just arranging these 6 people in a line would be 6 factorial. You happy? So 6 factorial ways of arranging these 6 people in a line with no conditions, okay? This thing in blue is the number of ways of getting this line in order such that Caroline and David do stand together. So therefore, if there's 6 factorial ways in total with no restrictions, this restriction in blue is the one that I don't want. So therefore, if I take it away from my total, in other words, 6 factorial minus this thing, then that should give me the thing which I do want. It's a bit like saying, well, this is the number of ways in total with no restrictions. This is the restriction I don't want. And of course, that restriction is all going to be buried in this 6 factorial. So therefore, all I need to do is take those two things away from each other and I'll be left with the thing which I don't want. So I start out with the total, take away the thing I don't want, and I'll be left with the thing I do want, okay? It's a bit like having a big cake, right? You start out with a big bit of cake, but you don't like the cherries on the top of the cake. Well, if you take the cherries away, you'll be left with the thing which you do want. It's exactly the same principle here. This is the thing in total, the 6 factorial, no restrictions, nothing like that. This is the thing I don't want. If I take it away, I'll be left with the thing which I do want, okay? So in other words, if I stick this into my calculator, I'm going to have to do 6 factorial, so I'll clear it first of all. I'm going to have to do 6 factorial, so 6 factorial minus, and I'll put this in a bracket just to be safe. I don't actually need to put it in a bracket, but I will do just to show you it's separate. So 5 factorial times by 2 factorial. And I'll put that in a bracket as well. Hit enter, and I get myself 480. So there's 480 ways of arranging the line such that Caroline and David do not stand together. Okay? Okay, so let's have a look at the next question then. So Alex has locked his bike using a 5-digit combination lock. So in other words, you've got a combination lock like this. Okay, and there's 5 digits on there. So there's 1 digit that can go there. You've all seen these kind of combination locks, right? There's my combination wheel. Then there's another combination wheel. And there's another combination wheel. Another combination wheel. And another combination wheel over here. So basically it's a combination lock and there's 5 like wheels on here if you like, and there's only 6 possible digits that can go in each of the 5 positions. So they'll be like the digits 0 to 5 here, then 0 to 5 here, and basically only 1 digit per position is correct. Okay, so basically I'll spin the wheels and only 1 digit on each of these wheels is correct. If you get the correct wheel, if you get the correct digit on each wheel, you unlock the Glock. Okay, so Alex has forgotten the Glock. Alex has forgotten the code to unlock his bike, so therefore he just tries some codes at random. What's the probability that he gets the code correct on the first attempt? Well, look, there's 6 possible digits that can go here, 6 that can go here, 6 that can go here, 6 that can go here, and 6 that can go here, okay? So in total, there's going to be 6 times 6 times 6 times 6 times 6, or 6 to the power of 5, possible combinations. There's 6 to the power of 5 different possible combinations. So let's see what that equals. So if I bring my calculator in, clear my calculator from my previous working, I'm just going to do 6, and I want to the power of 5. So I'm going to hit this button here. You see that button here? It's like X. There's a little square up there. That just simply means there's an empty power that I can put up there. So 6 to the power of, and you see my cursor goes up here, 5, hit equals, and it brings me back 7,776. So in other words, the total number of possible combinations is 7,776. All right, fantastic. So that's how many codes there are in total. Now, if I'm going to try codes at random, I want to know what's the probability that I'll get the correct code on the first attempt. Well, just remember to work out probability, so the probability of an event happening, so code correct on the first attempt, okay? I need to take the number of outcomes that I'm interested in. In this case, how many correct codes are there? Well, there's only 1 code. So there's only 1 digit per position which is correct. Therefore, there's only 1 code that is actually correct. So it's 1, okay? Then what's the sample space? Well, the sample space is the total number of codes that there are in total. Well, there's 7,776. We just worked that out. So therefore, the probability of getting the code correct on the first attempt is going to be 1/7,776. Okay, so in other words, 1 in 7,776. Okay, now let's have a look at part 2 then. How many wrong codes can I try such that at least 1 digit is correct? So in other words, I'm going to try codes at random, okay, and I basically got 5 different wheels. I want to know the number of wrong codes. So wrong codes means that, not all of the digits are correct. So there might be 1 digit wrong or 2 digits wrong. But I want to know the number of wrong codes such that at least 1 digit is right. How can I do this? Well, I've just established that the total number of possible codes to try, Okay, so the total number of possible codes to try will be 6 to the power of 5, or quite simply 7,776. That's the total number of codes that I could try. Okay. Now, how many codes are there that are completely wrong? Okay, so the completely wrong codes. So in other words, no digit in any position is correct. Well, if you think about it, in each position, there's going to be 5 numbers that aren't correct. Okay, so there'll be 5 numbers in this position which aren't correct, 5 numbers in this position which aren't correct, etc, etc. So therefore the number of completely wrong codes will basically be, I just select any of the 5 digits in each of the 5 positions that are completely wrong. Okay, so in other words, 5 times 5 times 5 times 5 times 5, or 5 to the power of 5. Okay, now if I check out 5 to the power of 5 on my calculator, so if I check out 5 to the power of 5, that will give me 3,125. So it's 3,125 completely wrong codes. In other words, none of the digits are correct on my log. Okay. Now, how many digits are completely correct? Because if you think about it, this is the total number of codes. This is the number of completely wrong codes. Okay. So what I'm going to go for here is a similar kind of thing to what I did in question 1. Because I don't know how to calculate the number of wrong codes where at least one digit is right directly, I'm going to do it like the complement. So I'm going to say, this is the total number of codes, 7,776. These are the number of codes I don't want, so therefore I'm going to take them away from each other. Okay, so I'm going to start off with 7,776. Take away 3,125. However, there's also one other event here that I need to take away. This is the total number of codes. This is the total number of codes where no digits are correct. Okay, but if you think about it, I also need the number of wrong codes. So I'm asking for wrong codes here. It says one code here which is completely correct. I don't want that counted in here. Okay, so completely correct codes, the number of completely correct codes is equal to 1. There's only one completely correct code. And considering that I want a wrong code with at least one digit correct, I need to take that one code away from here, and then I will be left with the number of codes which I'm after. So let's just quickly check that on a calculator. So I'm going to go 7,776 minus 3,125 minus 1, and that will give me 4,650 codes where one digit is right, but it's not correct. Okay, so 4,650 is the answer there. Okay, so let's have a look at question 3 then. So we've been told a society is going to be formed from 5 members. Now we've got a group of 10 women and 8 men who've nominated themselves to be elected for this society. So 5 of these people will go forward to be in a society. We want to work out the number of ways such that society can be chosen such that there are more women than men. Okay, now first things first. We need to think here, we're not actually ordering these people, okay? So we're just simply selecting people from this group of, in total, 18 people. So 10 women, 8 men, 18 people in total. We're just selecting 5 of them to go forward to be members of the committee. However, we want there to be more women than men. So because we're selecting them, we're not arranging them, we're not putting them into any kind of positions like chair or treasurer or secretary or anything like that. We're just simply selecting them. We need to say, right, okay, it's going to be a combination. Okay, so it's going to be N choose R. Okay, where N is the total number of objects and R is the number of objects that we select from that group. Okay, so it's going to be NCR, which remember, we could also write as NR like that. Okay, or we could write that as N factorial. So the number of ways of arranging those N people in a line, getting rid of the number of people that we don't choose, but then we're also going to have to divide by the number of people that we choose arranged, because we're not interested in those arrangements. So remember, that's how to calculate our NCR. So this is what we're looking at here, combination. Now, we want the number of ways that can be chosen such there are more women than men. Now, it is not, the trap is here to say, look, there's 18 people in total. So that's our N, that's the total number of people we're choosing from. And then we're just choosing, 5 of them. So it'll be 18C5, right? No. Wrong. So it's not 18C5 because we need to take into account this condition. There needs to be more women than men. So I think in this case, because there's a small number of people, start just by listing all of the different possible outcomes that we can have and then see if we can notice a pattern. Okay, there's not that many of them. So I think we can actually list all the different outcomes we can have. So let's suppose first of all, we have all women. Okay, so all 5 people are women. So 5 women, and that means there'll be 0 men. Okay, how many different ways are there, or how can we do that? So how many ways are there of choosing 5 women and no men? Well, have a think. There's 10 women in total, okay, and we're just choosing 5 of them. But at the same time, we're also choosing no men from our group of 8. Okay, so we're choosing 8, there's 8 men in total, and we're not choosing any of those men. Okay, now what we're going to do with these two things, well, we're going to multiply them. Why are we going to multiply them? Well, because it's an and situation. Okay, because we want 5 women and 0 men. We want both of those things to happen. You remember in probability, if you want it both to happen, you need to multiply those respective probabilities. Okay, fine. How else could it happen? Well, we could have 4 women and again, so and 1 man. That is totally fine, isn't it? That would still be more women than men. So that would be, well, okay, we start off with the 10 women, we choose 4 of them, and then we start off with the 8 men and we only choose 1 of them. Okay. How else could it happen? Well, we could also have 3 women and 2 men. That would also be fine because that would still be more women than men. So that's going to be 10, choose 3, times by 8, choose 2. Okay. Now we could not have the next one along, so we couldn't have 2 women and 3 men because then it violates the condition which we're trying to meet. We want more women than men. So therefore we can't have that. So these are the different possible ways that we have in total. Okay, so either all 5 are women and there's no men, we've got 4 women, 1 man, or 3 women and 2 men. Okay, and this is the number of ways of calculating each of those scenarios over here. Now, let's actually go through and calculate these in parts. So, okay, I'm going to bring up my calculator to show you how we calculate this. So let's do the first one, which is going to be 10, choose 5 times by 8, choose 0. So I'm going to clear my calculator. And I'm going to go 10, and I want my C. Now, C on my calculator is up here, just above the divide. So I'm going to go Shift, divide, and it brings up a C kind of in bold there. Then the next number is going to be the number which we're choosing, which in this case is 5. Okay. Then we're going to multiply that by the 8, choose 0, like so. So that's how to enter it on this calculator here. Now, if I hit enter, it brings me back 252 ways. So there's 252 ways in which we can choose all members of the society to be women and no men. Okay. Then if I do the same for the next one, just very quickly, so we're going to go 10 C4 multiplied by 8 C1, and that's going to give me 1,680 ways, such that there are 4 women and 1 man. And then finally, the last one, it's going to be 10 choose 3 multiplied by 8 choose 2. Okay, and that's going to give me 3,360 ways such that there are 3 women and 2 men in our society. All right, fantastic. Now, what are we going to do with these 3 numbers? What are we going to do with 252, 1,680 and 3,360? How are we going to combine these together to get our final answer? Well, if you think about it, this is now an or situation, okay? Because we can have this, or we can have this, or we can have this. We can't have them at the same time. So we can either have all 5 are women and no men, or we can have all 4 women and there's only 1 man. Okay, we can't have both of those at the same time. We can't have both 5 women and no men and 4 women and 1 man. We can either have this one or this one. They're mutually exclusive. They can't happen together. Okay, so therefore, if it's an or situation, we need to add all of these numbers together. Okay, so let's see what we get. So if I add all these numbers together, and in fact, I'm just going to make this a little bit smaller, just so it will fit on the answer line here. So if I add 252 to 1,680 plus 3,360, it's going to give me 5,292. So 5,292. Now you notice in this case that I used ANS here. Now the answer, the ANS, is this button down here. The ANS just simply says whatever was previously the answer in my calculator, just use that. Well, because the previous answer in my calculator was my 3,360, I didn't bother to type it. Okay, so that's the final answer, 5,292. All right, fine. Let's have a look at question 4 then. So we want to know how many distinct arrangements exist of these letters. So mathematics. So we've got M-A-T-H-E-M-A-T-I-C-S. So we want to find out how many distinct arrangements exist of these letters. Well, in total, would you be happy? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. Okay, so there's 11 letters which we need to arrange. So ordinarily, it would just be 11 factorial. right? So if they were all different letters, there'd be 11 factorial ways of putting those 11 letters into a line. However, we've got a couple of issues here. You notice that we have two M's, okay? In other words, if I was going to swap those two M's around in any of those 11 factorial arrangements, you would not notice. You wouldn't see any difference, okay? So therefore, I need to divide by the number of ways of arranging those two M's. Because if I split them over, you wouldn't notice any distinction, okay? But I notice as well that I've also got a couple of A's, right? So I've also got a couple of A's. So I need to divide by the 2 factorial ways of what happens if I arrange those two A's around. Because again, if I flip those two A's around, you're not going to notice the difference. Now I've also got a couple of T's here. So I've got a T here and a T here. So I need to divide by another 2 factorial to account for those 2 factorial ways of arranging the T's. And then all of the other letters are distinct. Okay, so in total, I have 11 factorial ways of arranging those 11 letters, but I need to account for the fact that I could flip any of the M's around, flip any of the A's around, or flip any of the T's around. Okay, fine. So now I can just stick this all into my calculator. So I'm going to type my fraction button, which is this one here. So I'll bring up my empty fraction. See my cursor is on the numerator. I want to put 11 factorial there. So I'm just going to type 11 factorial. Now I want to go on the denominator, so I'm just going to press the down arrow, which will move my cursor down here. Okay, then I'm going to do 2 factorial times 2 factorial times 2 factorial. Now in that particular example, I know that my calculator would work as timesing these things together. If you weren't sure, you could put a times in there just to be safe. But if I press equals, oops, I need to go back. Haha, speak of the devil. So the reason being is the 2 factorial. So I thought the calculator would recognize this. Clearly it hasn't recognized that I mean 2 factorial times 2 factorial. So I need to actually go in here and put the times. So to navigate across, I'm just going to use the side arrow, put the times, hit the equals, and I get a really big number there. But that's fine. I'm just going to write it all down as 4,989,600. So in other words, that's going to be 4,989,600 ways of arranging the letters mathematics. Okay, and it's got to be distinct. Okay, good. Okay, so now let's have a look at question 5. So question 5 is moving on from permutations and combinations and now looking at conditional probability. So just follow the advice which I've given you, which is if you're dealing with conditional probability questions, 9 times out of 10, draw a tree diagram. It will always help you. It is possible to do without, but I personally always draw a tree diagram and it will keep you out of trouble. So that's what I'm going to do here. So we've got a particular company, 90% of the employees who live more than 5 miles from work travel there by car, okay? We're told only 50% of the employees who live more than 5 miles or less from work travel by car. And it is known that 75% of the employees live more than 5 miles from work. So in other words, we've got a couple of things going on here. Either an employee lives 5 miles from work or not, okay? Or they travel to work by car. So those are the two things we're investigated looking at here. So either living more than 5 miles from work or not, or traveling to work by car or not. So those are the two things I'm going to draw. Now look at that first statement because it will tell you which order you have to draw your branches in. We're told that of the 90% of employees living more than 5 miles from work, so that has to come first, then they travel to work by car. So we're basically given the information in that order. So basically told, if you live more than 5 miles from work, so we already know whether they live more than 5 miles from work or not, then they travel to work by car or not. Okay, so therefore, that's the order it's got to come in. So it's got to be either living more than 5 miles from work or not. So let's say live more than 5 miles from work is going to be more than 5, okay? And this is going to be less than 5. Now I know it's less than or equal to, but I'm just going to call it less than just for the sake of space, okay? Then I'm told that from that I can establish whether they travel to work by car or not. So I'm going to say that's car or not car. And again here, if they live less than 5 miles from work, either you travel to work by car or you don't. Okay, so this is my probability tree here. Let's just focus on filling this probability tree out, then we can focus on the actual question in hand. Okay, so we're told that 90% of the people living more than 5 miles from work, so these people here, they live more than 5 miles from work, and then 90% of those carry on to travel to work by car. So in other words, the travelling to work by car bit, if you live more than 5 miles from work, you've got a 90% probability of doing that, okay? Which means you've got a 10% probability of not travelling there by car, because you notice the probabilities in the branches have to add up to 100% or 1, okay? Then you go on to told that 50% of those living more than 5 miles or less from work travel to work by car. So in other words, if you live less than 5 miles from work, then you've only got a 50% chance that you travel to work by car. So in other words, there's a 50% chance here, which means that there must be a 50% chance here. Okay? And then finally, you're told that 75% of employees live more than 5 miles from work. So 75% of the people live more than 5 miles from work, which means 25% don't. So you notice the way that I filled that out. I first of all figured out what order these branches had to come in. Is it whether they live more than 5 miles from work or not first, or is it driving to work by car or not first? So it came from that first statement. I'm told the information in that order. So I said, if you live more than 5 miles from work, then you travel to work by car. So that's the order it had to come in. And then I just used the fact that all the probabilities in the branches had to add up to 1. Okay, so that's how I found the complement probability there. So I'm just going to keep this tree diagram kind of quite small in the top corner. So I'm going to keep it over here, because now I've done the work, I can now answer the question. So I've said find the proportion of employees who travel to work by car. In other words, find the percentage or proportion of employees who travel to work by car. Well, are you happy there's 2 ways of travelling to work by car? Either this is travelling to work by car, or this is travelling to work by car. So either you live more than 5 miles from work and you travel to work by car, or you live less than 5 miles from work and you travel to work by car. So I'm going to say, okay, the probability of travelling to work by car will be equal to, well, first of all, the probability that you live more than 5 miles from work and then you travel by car. So that's going to be 75% times by 90%. You notice you times because it's an and situation. You want more than 5 miles from work and travelling to work by car. So those 2 things have to multiply together. And then you want or, because then the other situation, they can't both happen, right? Or you can have living less than 5 miles from work and travelling to work by car. So again, 25% times by 50% there. Okay, so let's stick all that in a calculator and see what we get if we multiply those through. Okay, so let me bring my calculator up. So if I bring my calculator up, I effectively get 75%. Now, there is a percentage button on your calculator if you wish to use it. Okay, this percentage button down here. So either you can convert 75% into a decimal, which is just 0.75, right? It's not that difficult. But if you did want to use a percentage button, it is there. So let's use a percentage button. We'll use 75. We go Shift, and then we want to type ANS to get the percentage. Then we're going to times that by 90%. Now, this percentage button may be slightly different on your calculator, just to have a little hunt around. Then I want plus 25%, so 25% times by 50%. All right, fantastic. Let's get equals. It comes back as 4/5, which gives me that. If I type percentage, it will give me that back as, actually I don't want that, so it was at 4/5, which would be 0.8. So there's an 80% chance, okay? There's an 80% chance. Remember, to convert from a decimal into a percentage, you just simply need to times by 100. Okay, so that's my 80% there. Okay, good, fantastic. Now we can go on and say, right, find the probability that an employee who travels to work by car, so that's given, we're given that an employee travels to work by car, and we want to find the probability that they live more than 5 miles from work. Okay, so I want the probability they live more than 5 miles from work, given they travel to work by car. Now you notice this is just simply conditional probability, which means we can apply Bayes' formula. So the probability of A, given an event B has already happened or been told to you, that should be the probability of B, given event A, times by the probability of A happening, all divided by the probability that B happens. Okay, so that there would be the way to calculate this probability. So I'm just going to make this a little bit smaller, and then let's actually figure out what needs to go where. Well, I'm basically saying that event A is travelling more than 5 miles from work, and event B is travelling to work by car. Okay, so in other words, I could calculate this by finding the probability that they travel to work by car, given they live more than 5 miles from work, times by the probability that they live more than 5 miles from work. So more than 5. Then I want to divide all of that by the probability that they travel to work by car. Okay, now let's go through this and do it systematically, and we'll refer back to the tree diagram we did at the top. So let's first of all find out the probability that they travel to work by car given they live more than 5 miles from work. Okay, so we're given they live more than 5 miles from work, which means we're looking at that position there, and then we're going on and trying to work out what's the probability that they travel to work by car. Well, there's a 90% probability they travel to work by car for the people that that live more than 5 miles from work. So that probability there is going to be 90%. Okay, so it's going to be 90% here. Then we're going to multiply that. So we're going to multiply that with the probability that they live more than 5 miles from work. Well, the probability they live more than 5 miles from work, that's 75%. Okay, so it's going to be 75% there. Then we're going to divide that by the probability that they travel to work by car. Well, didn't we just find that in the last question? Okay, in the last question we found the probability or the proportion of people travelling to work by car. That was 80%. So there's an 80% chance that you'll pick somebody at random who travels to work by car. So it's going to be 80% there. All right, fantastic. So now it's just a job of sticking all of this into your calculator. So let's have a look at this. We're going to type an empty fraction first of all to get our empty fraction up. Then we're going to go 90%. So 90% times by 75%. And then I want to go down on the denominator. Oh, make sure it's percent. There we go. Then we go down on the denominator, so press down. And I'm going to go 80% because we just calculated that. Okay. And if we hit equals, we get that. I'm going to convert it to thirds decimal. Now, if you're happy with reading off that as a percentage, in other words, 84.4%, that's fine. If you're not, just times that by 100. And you can find that is 84.4%. Okay, so the answer is going to be 84.4%. So let me just make that smaller. So there you go, it's 84.4%. Okay, so that'll be the final answer there. All right. Now, you notice in this case, we've actually scaffolded the question for you. So the people who asked this has actually scaffolded the question for you. So first of all, we found the probability that they've had to travel to work by car. Then they went on and said, using that, bedding that into the formula. So you've already got that part of the formula there. You can then go on and calculate the probability they live more than 5 miles from work, given they travel to work by car. Now, it is totally possible for them just to ask part 2 without asking part 1. Okay, so in which case it's just scaffolding the question, breaking it down for you, making it easier for you. But it is totally possible just to say, okay, given this information at the top, can you find the probability that an employee who travels to work by car lives more than 5 miles from work? Not an extra issue, it's just you don't have this already calculated, so you'll have to calculate this yourself. Okay, but it shouldn't be too much more difficult. All right, so let's have a look at the next question. So again, this is another probability question, okay, another conditional probability question. So we've been told that in an assembly plant, we have 3 machines, A, B, and C, and we're told the proportion which each machine makes. So 30%, 45%, and 25% of the products which each machine makes, okay? Now we're known, so respectively, by the way, respectively is kind of a word that comes up quite a lot here. It effectively means that the order in which I've told you that we have the machines is the same as the order of the proportion of each product that each machine makes. So in other words, A makes 30% because that comes first, then B makes 45% because that comes second, and then C makes 25% because that comes last. Okay, so it's the same as the order. Now it is known from experience that 2%, 3%, and 5% are defective from each machine. So basically 2% of machine A is defective, 3% of the products made by machine B are defective, and 5% of the products made by machine C are effective, because again you see they're respectively going on there. Now we're told that a product is selected at random. What is the probability that the product is defective? So first things first, I'm going to draw myself out a little tree diagram. Now this time I'm going to have 3 things. So A, B, and C is going to be the proportion in which the proportion of the products made by each machine. Now you may say, why are you doing it that way? Why can't you do it whether it's defective or not, and then the proportion for each machine? So why can you not do it in the other order? Reason being is because we're told the proportions of each machine, the proportion of the products made by each machine that are defective, okay? So in other words, we need to have each machine first and then whether it goes on to be defective or not. It doesn't make sense to have whether it's defective or not and then what proportion of each machine, because if it was the other way round, if it was a defective or not, there'd only be 2 things here, defective, not defective. Well, we've got 3 possible options for defective or not, okay? So we have basically A, B, and C, and we're told that 30% is made by machine A, 45% is made by machine B, and 25% is made by machine C. In other words, if I go out, select a product at random, these are the probabilities that I'll end up with the products made by each of the machines. Then it goes on and says, okay, is it defective or is it not defective? So I'm saying D is defective and then D dash is not defective. So D and then D dash. and then D, and then D dash. Okay, fantastic. So first of all, I want to find the probability that goes up here. So this is basically saying, what's the probability of being defective given it was made by machine A? Okay, what's the probability of being defective given it was made by machine A? Well, that's just 2%. We're told that. Okay, we're told that if it's made by machine A, there's a 2% chance of it being defective, which means there's a 98% chance that it isn't. Okay, that's pretty good. All right, then, if we go on here, this is basically saying, what's the probability of being defective given it was made by machine B? Well, we're told that probability. 3% of the materials made by machine B are defective. So that's going to be 3%, and that's going to be 97%. All right. And then finally, this probability here, you've guessed it, is basically what's the probability of being defective given it's made by machine C? Well, again, we're given that, that's just 5%, which means there's a 95% chance that it's not defective. Again, how am I getting that not defective? I'm just knowing the fact that the probabilities on the branches have to add up to 1. Okay, they have to add up to 100%. All right, fantastic. So this is going to be my little probability tree diagram, which I'll just keep stored away in the top left-hand corner up here. Okay, so I can quickly refer back to it. Now I'm in a position that I can actually answer the question. So we're told that a product is selected at random, and we're asked what's the probability that it's defective. So we basically want to find the number of different ways, or we want to basically find the probability it's defective, so probability of D. So first of all, we need to think, well, how many different ways can the product be defective? Well, first of all, it can be defective and it's made by machine A. Secondly, it can be defective if it's made by machine B. And thirdly, it's defective if it's made by machine C. So therefore, all I need to do is multiply the probabilities along the branches. So the first situation is it's made by machine A, and then it goes on, it has a 2% chance of it being defective. Then secondly, there's a 45% chance that it's made by machine B. And if it's made by machine B, there's a 3% chance that it's defective. And then lastly, if it's made by machine C, well, there's a 25% chance it's made by machine C, and there's a 5% chance that it's actually defective if it's made by machine C. So therefore, all I need to do is take these, take this, and I need to stick all this in my calculator. So it's going to be 30%, so 30% times by 2%, plus 45% times 3%, plus 25% times by 5%. It equals, that's the magic number. Again, I'm going to convert that to a percentage. So to convert to a percentage, just need to say, well, how many would that be in 100? That's going to be 3.2%. So that's my final answer there, 3.2%. That's what goes on the dotted line. Okay, let's have a look at part 2 then. We're told that if a product, or we're asked if a product was chosen at random, and if it was found to be defective, so that's given. We're given that a product that's chosen at random, if it's defective, so we're given that, what's the probability that it was made by machine C? So in other words, we want the probability that was made by machine C, given it was defective. Well, again, I can just use Bayes' theorem here. Now, I'm not going to write down Bayes' theorem again because we did it in the last question, okay? So it's basically going to be probability of D given C multiplied by the probability of C, all divided by the probability of D. So again, just using Bayes' theorem and just saying that's event A and that's event B, I can simply just recite Bayes' theorem there. Then I just need to go through and work out what each thing is individually. Well, let's have a look. Let's have a look at that probability there first of all. That's basically saying what's the probability that's defective given it was made by machine C? Well, defective, given it's made by machine C, there's machine C, and that's the probability it's defective. It's 5%. Okay, so that's the probability it's defective given it's made by machine C. So it's going to be 5% there. Okay, then we want to find the probability that it was actually made by machine C. Well, the probability it was made by machine C was 25%. We're told that. Okay. Then we want to divide that by the probability that's actually defective. Well, we just found that in the last question. It's 3.2% chance of being defective. So we can divide that by 3.2%. Okay, so let's stick all that in our calculator and let's see what we get out. Okay, scooch that over. Right, let's bring my calculator in, clear my calculator from the previous question. Okay, I'm going to set my nth fraction, which is this one here, and I'm going to go 5%, so 5% times by 25%. I'm going to go down the denominator, so I'm going to press the down arrow. Okay, now I could, if I wanted to, type 3.2% because that's my previous answer. Okay, but because I've already just calculated that on my calculator and I haven't done any calculation since, it means it will still be stored under A and S. So in other words, if for part 2, so if for the first part, I got a really kind of long, awkward answer with lots of rounding, to increase the accuracy, I can just hit A and S rather than typing that big, long, horrible answer in. Okay, now if I hit equals, it's going to give me my 0.09375. In fact, that's wrong. The reason being that's wrong, so ignore that, I can't put A and S, because I didn't get 3.2% as my last answer. What I actually got was 3.2, because remember I multiplied that by 100. So actually in this case, just to be safe, I'm going to put 3.2%. Okay, that's better. So it's about 9.375%. That's a bit better. So always ask yourself, does this answer make sense? If no, then go back and have a look. Okay, so 9.35% looks a bit better, so 9.375. Okay, fantastic. So that's going to be the answer for part 2. Now let's have a look at question 7, and let's finish off with question 7. So we're basically told that a class sits both a statistics test and a mathematics test. They sit both tests, okay? Then we're basically given the proportion of students for each of these different scenarios. So basically we're told 80% of the students that pass the statistics test go on to pass the mathematics test. Then we're told that 30% of the students that failed the statistics test passed the mathematics test, and then we're known that 40% of the students passed the statistics test. Now, what order? So basically going to create a couple of branches here. So branch here, then branches coming off here as well. Now, what order does things come in? Is this branch statistics or mathematics? And then go on to be statistics or mathematics. So we basically need to find out the order. Is it statistics first or is it mathematics first? We'll have a look. The clue is in the question, right? We're told that we know that this many people pass the statistics test, go on to pass the mathematics test. So in other words, the mathematics test has to come second. Okay, so I'm going to say this is passing the statistics test and this is failing the statistics test. I'm going to say S for passing the statistics test and S dash for failing the statistics test. Then likewise, M is going to be passing the maths test, M dash is going to be failing the maths test, and the same thing down here. Okay, fantastic. So now it's just a case of sticking this information into the question, into the tree diagram. So how many people, let's have a look at the first one. We're told 80% of the people that pass the statistics test, so these people here, go on to pass the mathematics test. So that's the probability that has to go on that branch there. So if you pass the statistics test, there's an 80% chance that you go on to pass the mathematics test as well. So it's going to be 80% there, which means that immediately I'll get some information for free. I know that this probability here must be 20%. In other words, people that pass the statistics test, 20% of them go on to fail the mathematics test. Okay, now let's have a look at the next situation. So 30% of people that fail the statistics test, these people here, go on to pass the mathematics test. That's the probability there. So 30% of the people that fail the statistics test go on to pass the mathematics test, which means 70% of people pass both tests, fail both tests, sorry. Okay, so I get that information for free. Then I'm told that 40% of people pass the statistics test. So 40% of people pass the statistics test, which means 60% of people failed the statistics test. So this is my tree diagram, okay? Just simply interpreting the question, getting it visual, and then from there, I think it's easy. Now you notice here, this isn't like a part 1 and part 2 question. We just simply asked, what's the proportion of students that pass the mathematics test? Okay, so what's the proportion of students that pass the mathematics test? So if I want to find the proportion of students that pass the mathematics test, okay, that's just simply going to be, well, how many different ways are there of passing the mathematics test? Either you pass statistics and mathematics, or you fail statistics, but you pass mathematics. Okay, so those are the two different scenarios I'm looking at. Okay, so in other words, it's going to be 40% times by 80% plus 60% times by 30%. All right, so that's the different situations there. So I just need to stick all of that in the calculator, and that'll be the proportion of students that pass the mathematics test. Okay, so let's have a look. We're going to bring in my calculator, and I'm just simply going to type, well, rather than typing 40% all the time, I'm just going to convert it to a decimal in my head. So it's going to be 0.4 times 0.8, which is 80%, plus 60%, which is 0.6, times 30%, which is 0.3. Hit equals, and I get myself 50% out. So that's going to be 50% there. And actually in this case, there's nothing else I need to do here. It's just simply what proportion of students pass the mathematics test. I don't have to calculate any given probabilities, don't have to calculate any conditional probabilities. This will be the answer there. So that's it. That's question 7.